This is Team B, Brad B, Ben Hobbs. The Mailbot is a line-following robot that's able to follow a predetermined black line. It will route its way to multiple destinations and check for packages that have been dropped off. After a few seconds of waiting, if nothing has been dropped off, it will continue on its way with a preference for left turns. Once a package has been placed, it'll wait and then calculate its route back home and then proceed. For the system architecture, we used 2 IR sensor arrays for a total of 16 individual sensors that we glued together and placed it at the front of the Roomba. And we also used a ultrasonic sensor to detect when the package has been placed down. For the IR sensor, we just had it so that if the middle sensors were detecting a value of 2,500 or above, we would put that as a black line, and that if the middle ones were detecting a black line, it would go forward. If the right sensors were detecting a black line, it would go right, and so forth. For the processing, we used an embed and a Raspberry Pi. The embed was attached to all our inputs, the IR and the ultrasonic, and they would communicate through the USB serial to the Raspberry Pi. Once the embed had detected a straight or a right or a left, it would send a 1 or a 2 or a 3. And the Raspberry Pi would then tell the Roomba to go straight, right, or left, and that's how we interface with the real world.
So the main thing that's driving this robot, or the core of this project, is the reflectance IR sensors that are in the front. So here I kind of describe how these IR sensors work and how we coded function to read it. So pretty much these IR sensors, first we put a charge on each of these pins. So for example, we'll just describe one of them right now. We put a voltage on one of those pins, and then we take it out and we start a timer, and then we start reading the pins. We keep reading them back and forth, back and forth, back and forth. And once eventually, based on the surface or any number of surface, the output voltage will eventually decay. Then we take that time, and then that's how we determine what surface each of those sensors are reading. For example, the black line we're tracking will produce, or will have a different timer compared to the white background that we're using.
So how the system flows is the embed samples every 40 milliseconds, checking for if the IR sensor or the sonar sensors have been tripped, and they calculate what needs to be done. The sonar, however, is only tripped whenever a black box has been detected, and the majority of the processing is done solely with the IR sensor arrays. After all of this is processed, it's sent to the drive motor, and the Roomba does those actions.
So these are the basic core commands and states that we kind of run into with a very high level summary. So the core commands that action do is basically you don't do nothing, you stay and you wait. You go straight for one cycle. You rotate left for one cycle, or you rotate right for one cycle. And now there are also some specific commands and states that we run into for specific actions. First is that how we detect end nodes, or pretty much places where potential package should be, where you need to stop and wait for something to be delivered or to be dropped on you. So we call it, basically it's how we detect these are basically black boxes, or 2 instances where all the sensors will trigger. So basically how it is that if we detect all the sensors, so all the sensors trigger, we move forward one cycle, and we check again. If all the sensors are still triggered, that means yes, we're at end node, and we play a song and we do all the actions that we normally do at end node. Now we have also corner cases where if you're at a T intersection or 4-way cross. Now here what we do is that if all the sensors trigger as well, we, just like the first one, we move forward one, And if only one of the sensors trigger, or the middle set of sensors, or none of the sensors trigger, that means we turn left. We keep rotating left until we see the black line again. So this is kind of saying, hey, we're making a decision to turn left here at a decision making point. Similarly, for intersections where it's sideways rotated T or the other way sideways rotated T, we do the same except for checking for all the sensors to be triggered, we check only the left half or the right half to be triggered. And of course, like before, we always turn left until we find the proper line to follow.
Here we're coming up on an intersection and we're going to turn left. No mail here.
Time to get curvy.
There goes my fragile mail.
Take me home, baby. We don't need to go left. Gotta get home before dinner. I got my mail.
Some of the challenges that we faced had to do with calibration. If we had differences in the background, if there was dirt or any black spots on the canvas, or if there was different elevations in the canvas, like bumps or dips, our sensors would read values that they shouldn't be reading, and it would throw the system off the route and into a state that it couldn't think its way out of. So to circumvent this, we had to tighten the spec, tighten the values that our sensor would be able to register. And here the robot detects the wrong route and needs to be recalibrated. Another challenge that we met was dealing with the intersections. If we didn't come at the intersections exactly straight, sometimes the left or maybe the right sensors would trigger, and instead of checking for a box or a T or a plus intersection, it would just make a left or right turn. And to fix this problem, we increased the sampling frequency, and we also let the robot have some leniency on letting it straighten out a little bit more before it came into these intersections. And also, after exiting the intersection, we give it some more time to straighten out. In this example, our robot is supposed to go home, so it's supposed to make a left turn, but Instead, it misreads the intersection and goes straight.